This week, we will focus on the properties of sound. This week's content will focus on defining sound, acoustics, and psychoacoustics, understanding the fundamental terminology associated with the musical terms pitch, volume, and articulation, exploring how acoustic instruments create sound. We will begin by focusing on the objective terminology associated with physics, such as waves, frequencies, and vibration. Understanding these basics is an important first step in discussing music technology concepts. First, let's talk about what a sound actually is. When we hear a sound, it is a result of a chain reaction of multiple elements working together perfectly to create a sense of sound occurring. A sound is a collection of waves that travel through a medium. For humans, that medium is air. The air molecules all around us respond sympathetically to a sound source because it vibrates. A vibrating source, such as a musical instrument, creates patterns of positive and negative air pressure in the air around it. Those patterns create the sound wave. A sound wave is a pattern of air pressure change that moves through a space. It is a physical phenomenon that occurs in the space around us. In this diagram on our right here, we can see a tuning fork at rest, therefore making no vibrations in the air and therefore creating zero sound. Once the tuning fork is activated and it vibrates back and forth, it creates a compression and rarefaction of waves in the air that generates a pattern that propagates through the air. Compression is when air molecules are compressed together. Rarefaction is when they pull apart. Much like in water, when waves compress and pull apart, air molecules do the same to create a sense of pattern of sound. So, acoustics, then, is the study of the properties and behavior of sound in the physical realm. Psychoacoustics, however, is another layer of acoustics that focuses on how the brain hears and perceives sound. The human brain can hear certain frequencies and is particularly sensitive to others. The human brain is only able to hear a certain range of sounds. It is important that we remember and understand this range. Also, the human brain does not perceive all sounds equally. Some sounds are louder than others. Our brains have been evolved to be very responsive to the sounds of human voices, and so our brains are particularly sensitive to that range of frequencies. We are going to explore the physical properties of sound that our brains use to recognize and perceive sounds. First, let's start with frequency. If a sound creates a pattern in the air molecules around us, it generates a cycle or a repeated pattern of one complete compression and rarefaction of air molecules. The speed at which the object vibrates determines its pitch, or what we call frequency, of the wave. Since we can measure objectively the amount of compressions and rarefactions over time, we can put an exact number on the highness or lowness of sound called frequency. Frequency is the number of cycles per second of a sound wave. It is measured in 1 second, and it is the objective measurement of a pitch. The higher the perceived pitch, the faster the frequency. The lower the perceived pitch, the slower the frequency. In our diagram on the right, we can see how the compression of air molecules is related to the height of the waveform and the lowerness of the waveform, but it's really the speed at which this process occurs that determines the frequency. Over here in this chart, we have a full cycle happening 1, 2, 3 times per this 1 second, and so therefore the frequency of this wave is 3 hertz. We use hertz to abbreviate cycles per second. It is the value we associate with frequency in an objective way. It is abbreviated capital H, small z, or small k hertz for kilohertz, because we often refer to hertz in the thousands. The human hearing range is important to understand as listeners and musicians. Humans are only able to hear frequencies between 20 and 20,000 hertz. However, many more frequencies above and below this range exist. There are many, many sounds in the world around us. We are only able to perceive pitch between 20 and 20,000 hertz. Sounds with frequencies above the human range are considered to be ultrasonic. Sounds with frequencies below the human range are infrasonic or subaudio. We will see how all of these frequencies are useful to us as audio engineers and creators of music. The height or amplitude of a waveform shows us how much energy or intensity a vibration has. That is related to the subjective measurement of volume. The amplitude of a wave determines the perceived loudness or volume of a sound. It shows us how intense the wave moves. Amplitude can be measured in decibels, measured small d, large b, and we can see in this diagram that these two waves are the same speed, but one has a higher amplitude than the other. The top one is quieter because it has a small amplitude. The bottom one is a louder one because of its large amplitude. We can measure decibels and amplitude in a few different ways, but a most useful way at this point is to use the decibel scale called sound pressure level, SPL. It is a way to determine how loud a sound is. It is a logarithmic scale of effective loudness relative to the threshold of hearing. 0 dB SPL is our threshold of hearing, meaning that it is our theoretical construct of silence. Keep in mind that if a human is alive and its brain is listening, it will always hear something. It will always hear the heartbeat or the nervous system or other small parts of the body moving around itself. So technically, there's really no such thing as silence, but we use this measure to give us a starting point for the threshold of hearing. Above this point, we have the sound of breathing, the rustling leaves, and at 30 decibels, a whisper or a refrigerator running, or other things like moderate rainfall and conversation, car traffic and trucks, hair dryers and helicopters, and so on and so forth. Once we get higher, we get into this area of pain, or where sounds can contribute to a sense of painfulness. Passing a police siren at close range or an ambulance will result in a very loud sound that is meant to pierce through a long distance. And so if you're close by, it makes a sense of pain. This is what we call our threshold of pain. That is 120 decibels SPL. Of course, sounds occur above this, and depending on your proximity to that sound, determines how painful or damaging that can be to your hearing. Equal loudness contours show us a combination of elements and help to summarize the concept of psychoacoustics. It shows us amplitude, frequency, and psychoacoustics in the same chart. On the y-axis, it shows us our sound pressure level dBs, and left to right, it shows us our range of human hearing from 20 to 20,000 hertz. Notice that these lines are curved, meaning that it is showing us how our brain perceives loudness. This chart shows how the human brain perceives constant loudness throughout the human hearing range of frequencies. It combines amplitude, frequencies, and psychoacoustics. Since loudness is subjective, this graph shows us how much more or less amplitude a frequency needs to be perceived by humans as equal in loudness. This is showing us that if this sound is to be perceived in the same loudness as this frequency, then the lower one will need to be amplified much more for it to seem as loud as something in this range. Notice that this range is right around where the human voice is, and most of our orchestral instruments that are melodic. This range cuts through or is picked up by the brain a lot easier than extreme low or extreme high frequencies. This chart can be very useful to help us understand how to mix many sounds together so they sound even. All of the sounds of an orchestra, a band, or even if you're mixing something like multiple layers of audio in any capacity, we need to know what frequency range they're in and how much energy to give to them so that everything sounds even. This chart shows us a little bit differently what the previous one was also saying, in that some of these things, low frequencies, low mids, mid-range, high mids, and high-end frequencies have different characteristics and need to be treated differently. This chart walks us through and shows us how much to boost and what to cut. It's a handy one-view guide to mixing. Finally, this week, we need to understand the amplitude envelope. The amplitude envelope of a sound is how we describe the way a sound begins and ends. It is the objective measurement of a sound's articulation. When we play an instrument, we can play a note quickly, we can play it legato, staccato, all kinds of ways. An amplitude envelope shows us exactly the amount of time it takes for a sound to begin and end. It is useful for us to see in a waveform how a sound behaves. It is the objective measurement of a sound's articulation. There are 4 parts of a sound's amplitude envelope: the attack, decay, sustain, and release. The attack is the time from silence to its peak volume. The decay is the time from peak to sustain. Sustain is the level of sustained sound, and release is the time from sustain to silence. Every sound has a unique amplitude envelope, including words and noises. Next week, we'll talk more about how all of these things contribute to our sense of difference in timbre and how things sound to us in terms of tone, color, and behavior, like amplitude envelope. So, to summarize, the subjective sensation of pitch is objectively measured as frequency in hertz. The subjective sensation of volume is objectively measured as amplitude, as decibels, and the subjective sensation of articulation is measured by the amplitude envelope, made up of attack, decay, sustain, and release points. Finally, this list of vocabulary is what we'll be responsible for in this week's quiz.